All right, so welcome back. We are in section 4, chapter 2, which is on the chain rule. And if you don't mind, I want to, before we get started in 2.4, I just want to show you something, a type of problem that you could see, and I just want you to be ready for it. So let's read. It says, determine the points at which the graph of f has a horizontal tangent line. Notice this question is not find the the equation of the tangent line. It's determine the points at which the graph has a horizontal tangent line. So really quickly, I don't want to dwell on the derivative process. But so you could use your quotient rule here. You could also break it up, the fraction the way I've done. And we have got to the derivative at this stage right here. So let's make sure you understand. So f prime of x will give you slopes at various x values, if they're defined, on your function, okay? But this time, we want to know the points where there's horizontal tangent lines. So a horizontal tangent line would mean that your slope is 0, right? A horizontal line has a slope of 0. So in this problem, it's telling you what to set the derivative equal to, right? We care about when the derivative is equal to 0. Okay, so at this stage, I'll finish this problem for you since I started it, but good luck trying to figure out what values of x would make the following, the right-hand side of the equation equal 0 in its current form. This is why I mentioned to you that it's in your best interest to rewrite without negative exponents. So we can rewrite this as negative 2 over x squared plus 2 over x cubed. Now, the reason why is because where we go from here is we want to get this into one fraction, right? So I have it equal to 0 here, I have it equal to 0 here. I want to combine these two fractions into one fraction. And to do that, I need a common denominator. So if I were to multiply by this first fraction by x over x, which is just multiplying by 1, then I would have a common denominator, right? I would have negative 2x over x cubed plus 2 over x cubed. Now I have a common denominator which allows me to combine my numerators. So 0, at this stage I would have 0 is equal to negative 2x plus 2 over x cubed. Okay, let's agree on something. In order to make a fraction equal to 0, I'll say this again because I want you to hear this. In order to make a fraction equal 0, let's you and I agree that you would have to make the numerator equal 0, right? 0 over 2 is 0. So if I want this fraction to equal 0, then the only thing that I care about is what would make the numerator equal 0. So coming off to the side here, so just all I got to look at is negative 2x plus 2, and I want to know what would make that equal 0. Well, I can factor really quickly. That would just be factor out a 2 or a negative 2, either one, doesn't matter. If I factor out just a positive 2, I'd have negative x plus 1. And now I think you and I see that if x is equal to positive 1, then I would have negative 1 plus 1. So I've succeeded. I know at this point when x is 1, right? So that, looking at the graph up here, here's where x is equal to 1. I know that there's going to be a horizontal tangent line, a slope of 0 at that point. Okay, but I really haven't answered the question. The question is determine the point or points where there's a horizontal tangent line. All I have is an x value. So what do I need to do with this 1? I need to plug it in somewhere. Well, I have two functions to choose from. I have the original function and I have the derivative. Well, if I want a point, then I want to know what's the y value given an x value. So I want to go to the original function. If I plug 1 into my original function, so f of 1, not f prime, I know f prime of 1 is just going to give me 0, but f of 1 is equal to 1. So what are the points? It's 1, 1. At this point right here, 1, 1, that's where there's a horizontal tangent line. Let's get back to the topic at hand, which is the chain rule. I just wanted to expose you to that type of question just so you're ready for it. So, okay, so there's certain, maybe you'll agree with this statement, there's certain benchmarks in mathematics that it's really hard to proceed if you haven't mastered that topic. For example, if you haven't mastered factoring, or at least pretty good at factoring, it's hard to continue to advance in mathematics, right? Because that's just a skill set that's just used over and over again. Now, as you move through the calculus sequence, right? Maybe you'll be with me through Calc 1, 2, and 3. The chain rule is one of these make or break type topics. It's one of these skills that you need to be good at because it's going to carry through. But let me go ahead and start with what do we mean by chain rule. So I'm not going to give you a proof. I just want you to make sure you understand what type of derivatives we are interested in. So here we have f of x is equal to x squared and g of x is equal to x squared plus 1. Now there's lots of ways to combine these two functions. I could f plus g, f minus g, f times g. But we have ways of dealing with each of those. But another way that we can combine these functions is through composition, right? We can compose a new function that we'll call f of g of x. In other words, we can take g of x and plug it in or substitute it in for x inside of your f function. And let's go ahead and, what would that look like? What would f of g of x look like? Well, it's fairly easy to do. It's just going to be something squared, and that something will be g of x. So x squared plus 1. Now, I understand that you could FOIL that out, but that's not the purpose here. The purpose here is let's just look at this function, x squared plus 1 squared. Okay, so if you wanted to take the derivative of that, I'm going to make a mistake. So I'll tell you what, I'm going to change my color. Okay, I'm going to make a mistake. But it's going to be a good mistake, and it's going to elaborate a little bit. So if I want to take the derivative of x squared plus 1 squared, let's assume the student, okay, thought, well, wait a minute, I've done stuff like this before. All I have to do is take the 2, bring it out front, and then subtract the 1 from the exponent. So let's assume that the student were to proceed that way. So in that case, you would have 2 times x squared plus 1 to the power of 1. Now, this is wrong, but I want you to see how close they are to the true solution. Let me change my color now. This is the actual solution. So the correct solution. So here is the correct derivative. 4x times x squared plus 1. And let's do me a favor. Let's just stare at these two for a second. Now, can you agree? So you can see that they're pretty close. Now, that's not good enough for mathematics, but it is good enough to try to say, well, what would you have to do to this wrong derivative? What would I have to multiply by in order to make it the correct derivative? Well, do you agree with me that if I were just to multiply by 2x, then everything would match up perfectly? Do you agree with me there? Well, now let me pose the question to you. What is the derivative of the inside of this function? What's the derivative of the inner part of this function? Exactly, 2x. Interesting. Let's proceed. Okay, so what is the chain rule? So depending on the textbook, depending on the notation of your professor, let me start by writing the rule for you that we're going to use. Okay, because I'm actually not going to use either one of these. The way we're going to do it is the following. F prime of u multiplied by u prime. So this is what I'm going to use over and over again for this section. Now, before we jump in, there's two things I want to do before we can just jump right in and start doing chain rule. The trick is choosing what you want to call u. So this first part here, we're not going to actually take any derivatives. I just want to help you with picking a good value for u. All right, so let's start with A. So if you want to use the chain rule here, you would want to allow u to equal x plus 1. Okay? So if you allow u to be x plus 1, then f of u would be 1 over u. Here's another equation where you would need to use a chain rule if you want the derivative. Notice that we have sine of 2x. Okay, you have changed the angle. In other words, this sine function is repeating itself twice as fast as it was before. It's a double angle. Well, in this case, you would want to let u equal 2x. So if u is 2x, then y would be sine of u. And radicals are another, especially if you have more terms, inside of your radical, that would be another type of chain rule. And in this case, you would let u be whatever is inside the radical, what we call the radicand. So 3x squared minus x plus 1. Part D is a little bit trickier. If you're gonna take the derivative of tan squared, we have to first think about. We would have to think about y as being tan of x squared. So notice that I'm just rewriting d. So now, what is a good u? Well, u would be tan of x. Okay, so at this stage, I've given you the formula, the definition that we're going to use for chain rule. I've helped you in the decomposition part, just choosing a good u. The last thing before we just jump in is I want to tell you why is taking derivatives of, let's come back over here, of composites, why is this of such importance? Well, think about the majority of the functions. If you're thinking about the majority of the types of functions you would encounter in the real world, almost all of them would be a composition. Think like for example, if you are driving home from work, the amount of time that it takes you to get home is going to depend on the traffic out there, correct? And the amount of traffic is going to depend on the time of day, because there are certain times of day, there's rush hour, etc. So do you understand then the amount of time for you to get home not only depends on how far the amount of traffic, which then depends on the time of day, and then you could continue this game where this depends on this variable is dependent on another. So the idea of composition of these functions is, well, I hope that analogy makes sense to you, that the majority of the functions that you are going to encounter are not going to be in isolation. They're going to depend on other functions. So this is why the chain rule, since it is what allows us to take derivatives of compositions, this is why we're going to need to master this little technique. So let's go ahead and jump in. So we want to find, I'm going to write the chain rule up to the top right. So f prime of u multiplied by u prime. All right. So first, let's notice that nothing in the problem says use the chain rule. So you could FOIL all this out. It would be x squared plus 1 times x squared plus 1 times x squared plus 1. It would be a lot of work. You could do it. Now, if this were x squared plus 1 to the power of 30, I guess you could still do it. But let's just learn a new technique, okay? So first thing to make sure you understand is let's be able to recognize form. So when it looks, what I'm really trying to say, if it looks like this, do this. But x squared plus 1 cubed, the form of your function tells me that I'm going to need to use a chain rule. All right, so chain rule begins, and let's get all the work out of the way. But it begins by, what do you want to call u? Well, here, just like hopefully you're starting to get used to the U-substitution, but if not, you'll be pretty good at it by the end of this video. So in this case, let's let u be x squared plus 1. Okay? Then what would f of u be? Well, if you were to plug a u in for x squared plus 1, right? Wherever you see an x squared plus 1, let's rewrite that as u. Then f of u would be u to the power of 3. Does that make sense? That here's an x squared plus 1. Let's just rewrite that as u. So now that's u to the power of 3. Okay, so the other two pieces that I'm going to need is f prime of u, and then I'm going to need u prime. So let's start. f prime of u, well, that's just the derivative of u to the power of 3. So that's easy enough. That's just going to be 3u squared. Now u prime would be the derivative of u, which in this case would just be what? 2x. All right, so when you get good at this, you'll be able to sidestep or skip, I should say, one of these intermediate steps. But until then, let's just put everything in the right spot. So I'm going to put f prime of u here, and then I'm going to put u prime here. So let's do that. So f prime of u would be 3u squared, and then u prime would be 2x. So what is this? This is going to be the derivative, y prime. All right. So at this stage, remember that, let's go back to the original problem. You would not want to give this to a client because although you were able to utilize this substitution, your client doesn't understand what the variable u represents, right? And in other words, they understand x and y because that's what their equation is expressed in. So we need to get back to in terms of x. So we use this substitution to make the derivative easy, but when all is said and done, we got to take x squared plus 1 and put it back for u. So let's do that right now. So that would be 3 times x squared plus 1 to the power of 2 times 2x. Now you have your derivative in terms of x. And the only thing left to do is just clean it up. We'll say 3 times 2x is 6x. So we have 6x times x squared plus 1 squared. Does that make sense? I hope that makes sense. All right, and let's try another one. This one's pretty similar to the previous one. In fact, if you like, it would be in your interest to pause the video and try this. But I'm going to just assume that you have done so. And if you learned a different method for the chain rule, that's fine. You can use your method of choice. I just need to be able to see your work. So let's begin. We want to take the derivative. I'm recognizing that this is going to be a chain rule. I can't stress enough that you want to be able to recognize when to use a chain rule. Okay. So I'm going to allow u to be 3x minus 2x squared. And now I'm going to plug a u wherever I see a 3x minus 2x squared. So f of u is going to be u to the power of 3. All right. What I need from here is an f prime and a u prime. So f prime of u and u prime. Let's do f prime of u. That's easy. That's just 3u squared. And let's go ahead and do the derivative of u. Well, derivative of 3x is 3. The derivative of negative 2x squared is negative 4x. All right. So f prime of u multiplied by u prime. Let's put everything in the right spot. So we're going to place f prime here. We're going to place u prime here. We'll write that prime symbol a little bit better. And here we go. So that's going to be 3u squared multiplied by, I'll go ahead and put parentheses, multiplied by 3 minus 4x. Now, at this stage, we need to back substitute for u. So remember I mentioned that you'll be able to skip one of these steps. If you, at this stage, you could automatically at this stage know that you put 3x minus 2x squared back in for u, right? So you might, after you have practiced this enough, be able to just jump right to this step here. And as time unfolds, I will probably do the same. I'll skip that step, but not right now. So times 3 minus 4x. Okay, so there's really, I mean, you could distribute the 3 if you wanted to. I mean, you really could distribute and clean all of that up. But I'm fine at this stage right here. It's in factored form. It's, if I wanted to set it equal to 0, it's perfectly set up. So we are done at that point. Okay, so we want to find all points on the graph. Let me read this, a good question. Find all points on the graph of the following function. All right, for which what? For which the derivative is equal to 0, and for which the derivative does not exist. All right, so the derivative equal to 0, the derivative does not exist. So, all right. So let me write f of x a little bit larger here. So that's the cube root of x squared minus 1 squared. Okay. So what I want to do is I want to get started using the U-substitution. I'm not going to, I'm going to end up with f being defined in 2 different ways, and I'm okay with that because we're going to proceed with our definition. And our definition is f prime of u times u prime. Okay, so let's see if you can anticipate where I'm going to go with this. So let me find a u, then I'm going to need an f of u, an f prime of u, and I'm going to need a u prime to make all this work. All right, let's see if you and I are thinking the same thing here. So what I'm going to do is, because I can imagine you thinking, well, wait a minute, do I choose u as x squared minus 1, or do I choose u as x squared minus 1 squared? But wouldn't that also need a chain rule? Well, you're onto something, but if you would have just noticed for a second that you can get rid of the radical symbol, right? In other words, what you would have is, let's maybe it's worth showing you something. Let's see if it looked like this. Do you remember how you can rewrite that as a fractional exponent? Well, that would be x to the power of, well, it is to a fraction. The index is always in the denominator. And then this 2 would be here. So this would be x to the power of 2/3. Okay, with that in mind, let's do the same thing here. So this would be x squared minus 1 to the power of, well, it's a cube root, so that's we know it's going to be over 3, and so that's also over 2/3. Okay, so the good news is, since I was able to rewrite it, this takes away a little bit of the guesswork as to what to choose for a u, because now I know to go with x squared minus 1. It also saves me from doing the chain rule multiple times, which sometimes you have to do. But I'm going to let u be x squared minus 1. So now f of u, I'm just going to put a u in for x squared minus 1, would be u to the power of 2/3. Let me go ahead and take my derivatives. So f prime, that would be 2/3 multiplied by u. And now if I have 2/3 and I subtract 1, right? It's like 66 cents, and you take away $1. I have negative 1/3. All right, I know that that's a negative exponent. I'll deal with it soon. U prime is now going to be the derivative of u, and the derivative of u would just be 2x. Okay, so let's go ahead and put everything in the right spot. I'm not going to draw the arrows for you this time. So this would be 2/3 u to the negative 1/3 times 2x. I'm going to go ahead and back substitute for u. So now I have 2/3 x squared minus 1 to the power of negative 1/3 multiplied by 2x. Okay, so this is my derivative. Let's go ahead and relocate this guy. So if this is my derivative, this is my f prime of x. Let's now, here in a second, I'm gonna erase the work that's above, but maybe if you're still copying, I'll just talk a little bit before I do that. I agree with you that I need to clean this up, but let's get back to what is actually being asked of us. Well, I have the derivative. I want to know, when does the derivative equal 0? So that's easy. I'll just be plugging 0 in or setting f prime equal to 0. But I also want to know, when does the derivative not exist? So interesting. Let's go ahead and clean all of this up here. Give myself a little bit of space. And let's go ahead and get started. So the first thing we want to do is we want to clean this up, because I don't know, it's really hard in its current form for me to be able to figure out what would cause the derivative to equal 0 or what would cause the derivative to not exist. What I want to do is I'm going to go ahead and distribute this 2/3 to this 2x. Right? So that would be 4x over 3. So that's 4x over 3 times x squared minus 1 to the power of negative 1/3. Okay, so any base with a negative exponent, I want to move. So make sure you understand that this is my base, the x squared minus 1. All of that is being raised to the power of a negative exponent. So when I'm going to move this, and it's going to turn the negative 1/3 to a positive 1/3, but I want to make sure I move the entire base. So what am I trying to say? Then what we would have is 4x is what would be left in the numerator. And in the denominator, I'm going to have 3 times x squared minus 1 to the power of positive 1/3. All right, so at this stage, we have enough to answer the question. So let's rewrite the question. So when does f prime of x equal 0? And I'm going to show you the trick here, if you'll listen to me. And when does f prime of x not exist? All right, so that is, we'll call that part A and part B. I'll tell you what we'll do is we'll take a break after I finish this problem, and I'll do a part 2 to this, this chapter, section. All right, please listen to me. I can make life so easy on you if you just listen to me. See, once you have simplified your derivative into this this fraction, this rational function, watch how easy this is. So again, if you want to make a fraction equal 0, you would have to make the numerator equal 0. If you want to make a fraction not exist, now in this case we'll assume that we're not worried about negative numbers inside of square roots or fourth roots or anything with an even index. But let me say that one more time without the tangent. If you want to make a fraction equal 0, then make the numerator equal 0. If you want to make a fraction not exist, make the denominator equal 0. So watch what I'm going to do here. So when they ask me to figure out what would make the derivative equal 0, notice I'm going to only worry about the 4x. Right? How could I, that's the numerator. How could I make 4x equal 0? Well, there's only one way, or there was only one x that would make 4x equal 0. And that's if x equals 0. Does that make sense? So when x equals 0, you have a slope of 0. Okay, we'll come back to that point in just a second. Now let's do, when would the derivative not exist? So I want to look at the denominator. So the denominator is 3 times x squared minus 1 to the power of 1/3. And if I can make that denominator equal 0, then I know my derivative does not exist. And you should be able to spot it from here that if you choose a x equals 1, you would have 1 minus 1. If you choose x is equal to negative 1, you would still end up with 1 minus 1. So that would zero out the denominator. So if you choose x is equal to plus or minus 1, that would cause division by 0 in your derivative. That would mean that your derivative does not exist. Okay, so we haven't answered the question really in its entirety. I mean, we do have all the hard work done. But the question asked, find all points. Well, I have 3 x values, right? If I have 3 x values, that should be 3 points. So I know I have an x value of 0, an x value of negative 1, and an x value of positive 1. I just don't know the y values, right? So all I have to do, and all you have to do, is just understand that you need to plug your x value into the right function. So if you want a y value, then plug 0 into the original function. If you want a slope, you plug 0 into the derivative. Okay. So I'm going to go ahead and leave this the way it sits. It's all you on your own time. You can plug 0 in for x, plug negative 1 in for x, plug positive 1 in for x, and that would give you everything that you need to answer this question. So, as I said, let me go ahead and take a quick break. I'm gonna grab a little bit of something to drink so my throat clears up, and I will be back for a part 2.